The topic for this will be independence. Do not confuse it with the with some other independence. This is independence of events. Independent events, I'll write. Okay. Now you have seen a lot of examples that we did so far in conditional probability. In that we said that something happened. Now what is the probability of this thing? Okay. So we conditioned on something. Okay. We also read about unconditional probability. So if I say probability of E, so this is unconditional probability. There is no condition given to me. Now if I say probability of E given that F happened, something happened. So what is the probability of E now? So most of the times you will see that some events are not related even. So if I see that probability of E given F, if it is again equal to P of E, okay, something like this. So when when one event happened and a conditioning does not affect the actual event, so we say that these events are independent. Okay. So again, to reiterate it, what I'm saying is I'm saying if there is an event and because of that, if one event happened and it did not affect the happening of other event, so that's called, these two events are called independent events. So two events are said to be independent. So how I can write it? If one event happened, let's suppose event F happened, and probability of, then we say what is the probability of event E? It still is probability of E. Now even if you see in the conditional probability that it was probability of E given F, that was equal to probability of E intersection F divided by probability of F, something like this. Okay. Now here what are we saying is that we are saying if you take this probability now P of E intersection F. So P of E intersection F, this can be written directly like this, probability of E multiplied by probability of F. Okay, that's how we got this formula. So if you see, this is by definition. This thing is by definition. I'm saying what is the meaning of independence. So from there I'm saying probability of E given F actually was equal to probability of E intersection F divided probability. This can be written as probability of E probability of F divided by probability of F. Okay, that's how these got cancelled. So this basically means this is equal to this. That's what I wrote in here. This is the definition of independence. If two events are independent, then the intersection E intersection F is equal to their individual probabilities. That is the mathematical definition. Why is this definition important? There are many things why is the definition important. So we'll get to that also. First, I'll give you an example. Let's suppose we have a biased coin. Okay, we're tossing coin and we're tossing this biased coin 3 times. So what is the meaning of biased coin? Now probability of head is more than probability of tail, or probability of tail is more than probability of head. Let's suppose probability of head is some p and probability of tail is obviously then 1 minus p, because these events are complements of each other. If I construct that tree diagram, sequential tree, so the first thing is head and tail, and the second thing also is head and tail. Third thing will be head and tail. So this is the tree that we will have. Okay, so in the first I'll say right here it is head, it is tail, head, tail, something like you know this. I'll just write the probability. So here let's say this is probability p, this is probability 1 minus p, this is p 1 minus p, again p 1 minus p, p 1 minus p, okay, and the upper side is the head and lower side is the tail. So if I have to write, this is head, 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 this is, I'll write it like this. For the 4 I have head, then for the 4 I have tails, head, tail, tail, head, head, tail, tail. Okay, and these are the 8 leaves. This is the first leaf, second leaf, third leaf, this is my fourth leaf, fifth, sixth, seventh, and eighth. Okay, now this coin is biased coin. So that's what I say, that probability of head is p and probability of tail is 1 minus p then. So what I say is I am telling you that if you have to compute let's suppose probability of second head given that first head happened. Okay, what is the probability that second head happened given that first head? What's the probability of second head getting a second head on toss of coin given that the first head happened? So which branch will it lie on? So first this is head, this is head. Okay, this again is head, this again is head. Now I am saying that the first head happened, that means this event happened, this event happened. So this over here happened. Okay, I'll write it like this. The first event happened. So what is the probability that the second will be head? So that's what I'm saying. So what should be the probability of this? Can anybody give me the answer for this? Or even if I can write, what is the probability that, let's suppose I'll write probability of THT. This means the first toss was tail, second toss was head, and third toss was again tail, something like this. If you have to compute these sort of things, so we can compute this. So here I can write it, I can just expand this. So I can, if I have to expand this, so this will be probability over here. So this is probability, this happened first. So this happened, and second is also this happened. So this will be P multiplied by P. Okay, this will be P square. So how many of you agree with this? The first happened, given the first happened, second. And now what I am telling you is, I am again telling you that what is the probability that, let's first compute different sort of probabilities so that I'll prove that these events are independent. I'll tell you to compute different probabilities. Okay. So the first thing is probability of tail, head, tail. So how do you compute this? So probability of tail, because we'll write it 1 minus P. This will lie in this branch. Probability of tail, head and tail. Tail, head, tail is this much. So tail, how to reach this? So you will go from here, this path, this path, this is 1 minus P, P, 1 minus P. So 1 minus P, P, 1 minus P. Okay, is everybody with me?
Yes, sir.
Okay, so what is, if I say what is the probability of one head? So probability of one head. So where is the one head? So here we get one head. So if you see, if we exactly want one head, so TTH, this is one head probability, and again I think this is one head, and here we have one head. These are the three situations where we get one head. So what's the probability here? So probability one head. So how will I write it? Probability of this plus probability of this plus probability of this. So if you see each of this over here, so this is P into 1 minus P into P plus again 1 minus P, P, 1 minus P. So can I write it like this? This 3 times P into 1 minus P whole square. Can I write it like this? Answer me, answer me. I cannot see the screen.
Yes, sir.
So if you are convinced, then only tell me the answer. So what I am saying is probability there is one head. So in the three toss there is one head. So I said that there is this, this, and this are the three situations where we'll see one head. So how to get this? So either we should go from this path, this, and this. This is P, 1 minus P, and P. So this over here is P, 1 minus P, and 1 minus P. Again same for this also, P, 1 minus P, into 1 minus P. Similarly P, 1 minus P, into 1 minus. So this is 3 times. So what I am writing is, instead of this I am writing it 3 times P 1 minus P whole square. Probability of getting one head. So now this is, this thing over here, if you see it, this is multiplicative rule. This is multiplicative rule. And this over here, if you see it, this is total probability. Again coming up with the both of the all of these things again. Now if I say that what is the probability that first toss is head, first toss is head, given that there is one head. Okay, now in the three tosses I am saying I know that there is one head somewhere, but what is the probability that first toss will be head? Are you understanding the question? The question here is, what is the probability that the first toss is head given that one head appeared somewhere? That means one of these three events happened. Either this, this, or this happened. That is what is the meaning of this one head appeared. But now my question is, what is the probability the first toss will be head? So there is only this option if you see. So HTT. So this is HTT. So this is THT. So this is TTH. So in the first, so here we have three events. So among these three, we have one head. So now what is the probability that the first toss will be head? So that is this event. So how much will be it? Zakir?
Yes, sir. It will be P into 1 minus P whole square.
If you directly see, these are 3 events. It will be 1 by 3. Don't you say it will be 1 by 3? Because now you are conditioning the things. Now your whole sample space is this much and everything is equally likely. Are you understand the point? The point was, what is the probability that the first toss is head given that one head appeared? So in these three conditions, one head appeared. In these three conditions, we had one head. So now each of these has probability 1 by 3 if the event happened. Now I am saying this, what is the probability of this now? This is 1 by 3. So you can also use the Bayes theorem for this. So how many of you understood that probability will be 1 by 3?
Yes, sir. Got it.
So if now we can use Bayes theorem, we'll see if the Bayes theorem agrees. So we also saw intuitively, and we'll see with the Bayes theorem. So this will be probability of H1. First there will be head intersection, one head. Okay, divided by probability of one head. Okay, I just expanded it by using this. So what's the probability that first will be head, and given there will be one head? So what's the probability of this? This will be P into 1 minus P square, which Zakir said. So Zakir said for this event, the probability will be P into 1 minus P square. Okay, so what's the probability of one head? So this is this much. So this is divided by 3 P into 1 minus P square. So this will get cancelled. This is equal to 1 by 3. How many of you understood this example? How many of you understood this example?
Yes, sir.
Zakir, Asrar?
Yes, sir, got it.
So what I have to say is, now this is special example. Why is it special? If you see what is the probability of second head given that first head happened, you can see that this is one. This is P. So if, for let's suppose, if I say that what's the probability that first head happened? Okay, if you see this is our head, this is our head. What's the probability that second will be head? So second will be head. This is again P. If you see it's P. If it is even tail, if the first toss was, let's suppose, tail, and what's the probability that second will be head? Again P. So are you seeing this probability of first toss being head? H1 is head and H2 is the second toss is head. So this is P. How many of you agree with this? If you see the diagram, so again making that diagram a little bigger. So this is something like this. This is really important to understand. So that's why I said if you understand conditional probability and these multiplicative rule, and you understand 30% of the probability, I think even more than 30% of the probability. So this is, so if you see this line, this is probability of head, this is probability of tail. So I am saying probability will get head 2 given that head 1 happened. So head 1 happened means we walked through this path. Okay, now what is the probability that head 2 will happen? Head 2 means go this path. This is again P. That's what we wrote here. So if you see the previous diagram, we wrote P P P. So here it is P. So I am saying if it is a tail, so tail means you're going this path. So what is the probability that head 2 will happen given that the first toss was tail? T1 was tail. So if you see the subscript, I am writing the toss number. So Ti means ith is tail. Hi means ith toss was head. So if the first toss was tail, so this is this way. So here and this. So if the second probability of second being head, so this is this much. So this is again P. So do you agree with this? How many of you agree with this?
Yes, sir.
Are you able to see this? Everyone please see it. Focus over here because this is really important. So I am saying this experiment is somewhat special. Why is it special? So if you see that, what's the probability of head 2 given head 1? Given that head 1 happened, given that in the first toss we got head 1, that is equal to P. But if you see, what is the probability that head 2, that the second toss will the head will appear, given that first toss was tail, it is again P. So did you see that on the second toss, so head will appear, it does not depend on the what happened first. So are you seeing that? So it doesn't matter what happened first, whether tail appeared or the head appeared. The probability is same for both of these events. So probability, if you see probability of H2 given H1 is also P. So probability of H2 given T1 is again P. So that is if head happened in the first toss or tail happened in the first toss, second event or second head, it is not getting affected. Okay, or I can write what is the probability of head again. If I write just probability of head 2, so what will the probability of head 2 if you see it? So probability of head 2, where is the second toss head? So second toss is head in many events. So second toss is head in, probability of first toss was head multiplied by probability of head 2 given H1. Okay, plus probability, let's suppose this was tail 1 multiplied by probability H2 given tail 1. This is by using total probability. Okay, now if you just expand it, so what is the probability of head multiply a probability of head 2 given head 1? This is 1 minus P, and this is P into 1 minus P. Okay, and if you just add this one up, so you will So plus you will add this, and right now you will get the P again. So for this you will get P. If you add these terms up, so you will get P. So my point was, so what did I write? So I wrote probability of head 2 given head 1, or probability of head 2 given the tail 1 appeared. In the first toss, tail appeared. This is P. This is also P. Then I said that what is the probability that what's the probability of head 2? Okay, even on these conditioning, when I calculated, so this came out to be P. So for both of these, so if you see, this came out to be P. So this is also equal to P. So these things are also equal to P. Okay, how many of you understood this?
Yes, sir.
Okay, so this over here, I'll write it. This is directly equal to P. You can compute this. This is equal to P. This whole probability is equal to P. So here, if you see that, so the whole point of telling you this example was that whatever happened in the first toss, it did not impact the probability of getting second toss's head. Okay, now these you can claim that these two tosses are independent, or even you can claim it for the third toss also. Okay, so the tossing of coin each time are independent events. Are you understanding this? So what is the meaning of independence? Mathematically, we said that if happening of one event does not impact the happening of other event. That's what we showed mathematically. I said that what is the probability that we'll get in the second toss we'll get head, given that in the first toss we got head. So we compute that is equal to P. So what's the probability that we'll get second head, in the second toss we'll get the head, given that in the first toss we got tail. So that's again P. If you compute what is the probability of second head, that's also equal to P, because by using the total probability, if you compute that, so that is from here, probability of head 1 multiply probability of head 2 given head 1, probability of T1 given that probability H2 given T1. So this, if you compute, this is also equal to P. So these things also equal to P. So that is the definition of independent events. So in nutshell, if you have intuitive idea, intuition tells you that if happening of one event does not affect the happening of other event, then we call these events as independent events. Is it clear?
Yes, sir.
Yes,
Okay,
sir.
so that is the definition. So if I write the definition now again to rehearse the definition that we saw, I think when we started. So probability of B given A, that was equal to probability of B, or we can write probability of A given B, that is equal to probability of A. These two are said to be independent events. So if I say A and B are independent, so we can just, instead of these two things, we can just write this. We can write probability of A intersection B is equal to probability of A multiplied by probability of B. Why? So what's the reason? So technically this definition is much better. So this also can be treated as definitions. Okay, so happening of A does not impact B. So if the probability of B was probability of B, even if A happened, there is no change in probability of B. So if B happened, there is no change of probability of A. So but this definition is still better. Why? First, because you only need to write one statement, and you can just get these two statements out of this one statement. So this is the first advantage. The first thing is that you can get this, and you can as well as get this. So you can get both of these. So from this definition alone. So I'll write this. This definition is mathematically, I won't say accurate or something, but this is mathematically better definition, because it is symmetric with respect to A and B. Symmetric with respect to A and B. Because you don't need to write separately, because you can get this also from this, you can get this also from this. Okay. So even if you expand this, so here you assume that if let's suppose you write P of A given B, and this is equal to P of A. Here you assume that P of A is not equal to 0. You will have to assume, otherwise there will be some problem. If you see that when you write conditional probability, you write probability of A intersection B divided by probability of A. So here you wrote that this should not be equal to 0. Otherwise there will be problem in definition. In here you can say that probability can be 0 also. That's one again a mathematical thing that we can use. So for the first thing, it is symmetric. You can get both the definitions. So it also implies that both of these things are implied. And the second thing is, you can also here assume that probability of A or probability of B can be 0. So in this definition, if you write those things as to be equal to 0, then it will violate that conditional probability definition. So it is better mathematically. This definition is some sort of like mathematically better than writing these two. So if you have to prove any two events are independent, so what you will write is, you will say that if probability of A intersection B is equal to probability of A multiplied by probability of B. So it is not like this. You write probability of A, then you will write multiply probability of B given A. Okay, because this you know that is equal to probability of B. Okay, and you just have to check this. This is the definition of independence. Now there's again one more thing that people get confused. People get confused between independence and mutually exclusive. These are two entirely different concepts. So I'll just clarify the difference between mutually exclusive and independent events. Okay. So what is the meaning of mutually exclusive? Mutually exclusive means if in the terms of set theory they do not have anything in common. Okay, so if they don't have anything in common, does it mean independence? So what is the meaning of independence? Independence means if one event is happening, it does not affect other event. It does not tell you anything about the happening of other event. Let's take an example to clarify this. Please focus here so that for the whole life you will get this example settled in your mind. So let's suppose this is our whole sample space, and now this is our event A and this is our event B. Let's suppose this is our event A and this is our event B. So are these events mutually exclusive? So what do you say? Are these events mutually exclusive? How many of you say that these events are mutually exclusive? If you understood this mutually exclusive.
Yes, sir.
Yes, these events
Yes,
are
sir.
mutually exclusive. Why? Because they're disjoint. So mutually exclusive means that there is no commonality in that. Mutually exclusive means probability of A intersection B should be equal to 0. This is the meaning of mutually exclusive. So there is no intersection between them. So are they independent though? So are they? We'll see. Are they independent? So this probability of A will be greater than 0, obviously because it's a para sample space, and probability of B will also be equal to greater than 0. This will be greater than 0. So probability of A multiplied by probability of B, how much will it be? So this will be greater than 0, obviously. So but we for independence we need the probability of A intersection B should be equal to probability of A multiplied by probability of B. So now you saw that this is equal to 0 because they are mutually exclusive, and this is equal to non-zero. And now these things are not equal, so they are not mutually exclusive. So they are not independent. Sorry, they are mutually exclusive but not independent. So, but they are so dependent. Why are they dependent? If A happened, that guarantees you B would not happen. That's why they are dependent. Why are they dependent? Because if somebody told you that A happened, you are sure that B will not happen now. It's like coin. If head appeared, tail won't appear. Okay. So how many of you understood what is the difference between mutually exclusive and independent events? Mutually exclusive just means that there is no common element between them. An independent event means that one if event is not affecting the happening of other event. So this is the difference, main difference between these two things. Okay, we can even do the questions based on this, but first we'll again see other things that are there in mutually in this independent event is. So okay, we'll see those things also. Let me pause for a second. If you have questions or something like that, I'll take them. So here now we'll move on to the next topic, that is if we are given that two events are independent. Let's suppose we are given events A and B. A and B are the events which are independent. A, B events are independent. Now what we can say is, the question is that is the complement of this events independent? Okay, so what I mean is, like, is A and B complement also independent? This is what I have to see. So I am given this is my given statement. Now the heading that you can write heading of this topic is that independence of event complement. So independence of complementary events. So here this is given to me. So what I am given is this much. So I am said that if A and B are the events which are independent, now I need to tell that are A and B complement, are they independent also? So this is what I have to see. So intuitive argument can be, let's suppose this is my A, okay, and let's suppose this is my B. Okay, so if I'm saying that if A and B are independent, let's suppose. So if happening of I can tell you intuition also. So we can also give the, let's suppose we'll first try to give it mathematical proof and then we'll see the intuition proof. So let's write the formal proof first, because first I believe I should prove the things mathematically, then I should try to prove intuition, because sometimes intuition is wrong. That's why I go other way around. I first try to build the things mathematically, And then if these things I have to tell intuitively, then I have to create an example. Sometimes intuition goes wrong, then it is difficult to like counter them with mathematics. So that's why first we'll see a formal proof. So how to prove this formally? So let's suppose we have this event A. This can be written as like this: A union B, and then I can write it union A intersection B complement. So if I have two events A and B, these are my two events A and B, I can write this A like this. So A is this, so I can write it A union B, okay, and this is A intersection B. Sorry, this is not union, this is intersection. So if I write A intersection B, this is this much, okay, and then A intersection B complement. So B complement is everything that's outside B, and what is the intersection of A with? This is this much. So can I write A is equal to this? Do you agree? I can write it like this. Do you agree with this?
Yes, sir.
So how am I proving the things? First see my thinking also. So when I'm proving something, do not take them as steps. So why am I writing this step? Sometimes it becomes like really tedious to see. So independence means I know that probability of A intersection B is equal to probability of A and probability of B. Isn't this the thing? This is given to me. So actually what I have to prove? So I have to either prove or disprove one thing. So I want to see if these two things are independent. I have to check if A intersection B complement, is it equal to probability of A multiplied by probability of B complement? This is what I have to see mathematically. So if somebody said me that A and B are independent events, are A and B complement independent? This is what I have to prove. So here this is what I am looking at. That's why I wrote A like this. I first expanded A. Okay. Now you know that these two events are disjoint. By action of probability, I can write it like this: probability of A, this is equal to probability of A intersection B plus probability of A intersection B complement. Can I write it like this? So this, as this is given to me, this is independent. So I can write it like this: probability of A multiplied by probability of B. See how I prove the things. Please and please have a look at this, because I'm not proving this only. So I'm telling you how to prove things. If somebody told you how to prove a thing, because seriously I even don't know myself. So when I start the proof, I was not knowing that if A and B complement are independent. So I start with this because this is given to me, and this is the thing I want to confirm: is it equal or not? So I started with expanding the A. I said A intersection B can be written like this. Now I use the axiom of probability. I can just expand these things out. So here this thing is given to me. So this thing is given. This thing is equal to probability of A minus probability of B plus this thing I don't know anything about. So probability of A intersection B complement. This is my this part. Okay, and this is probability of A. So I'll turn this on the other side. This will be probability of A minus probability of A into probability of B. This is equal to probability of A intersection B complement. So this I can rewrite it like this: 1 minus probability of B into probability of A. Can I write it like this? So this will be probability of A intersection B complement. So here if you see, this is probability of B complement. Yes, this is equal. So the both, if two events are independent, so that means one event is also independent of the complement of other event. So have you seen the formal proof? How many of you understood this proof? Riyan, Amir?
Yes, sir. Got it.
Per se, I'm not proving the thing only. So what I'm doing is I'm telling you how to prove things. So actually what I was given is I was told that A and B are independent events. The first thing I wrote at mathematics, this is the thing that is given to me. Okay. Then I was said, is A and B complement independent? So this is the thing I have to check. Is A intersection B complement equal or not equal to P of A, and P of B complement should be, it should be B complement here. This is the thing that I have to see. So what I did is I first showed I can break this A into A intersection B and A intersection B complement. So now both of these are independent, both of these are mutually exclusive, they are disjoint. So I can write by probability axiom, I can write it like this. Okay, probability of E is probability of this plus probability of this. Now this I know, this I can expand because this is given to me. Probability of A into probability, this I do not know, this is what I want to find. And then I just did some algebra here and there. I got to know the probability of A multiplied by probability of B is equal to probability of A intersection B complement. So this tells me that these are independent. Is it clear? Now we can look at the intuitive idea. So it should be other way around. Do not build the intuition and then prove the things. First prove the things, because mathematics is always right. Okay, if you do something with maths, it's always, intuition can be wrong. So now it is better to build an intuition now. Okay, so if A and B are independent, So what I'm saying is A and B are independent. That is probability of A intersection B is probability of A multiplied by probability of B multiplied by probability of B. This is what I have. So intuition tells me that if now we have this event, let's now build the intuition. Now I'll see the intuition, because now I am at least convinced that A and B complement is also independent. Now I have to build my intuition accordingly. So this is my event A. Okay, this is my event B. Let's suppose this is A and this is B. Okay, let's suppose this A and B, these events are independent. That is P of A intersection B. So this portion over here. So whatever probability is of this is equal to probability of A multiplied by probability of B. Now I will see if it is given as B complement. If I have been given A and B complement, A and B complement means this whole is A. Okay, and what is B complement? So B complement is, I think, this much. So this is B complement. A intersection B complement, and whatever is outside this is also B complement. Okay, do you agree on this? So
Yes, sir.
see,
Yes, sir.
so see if I'm writing it correctly. Okay, now I have to see, are they, like, intuitionally can I see they are independent? If I am claiming that A and B are independent, that means probability of A intersection B, this is equal to probability of A multiplied by probability of B. This is equal to this. So probability of this portion is equal to, you take this portion and you multiply it with this portion. That is this. That is equal to this. Like, it's hard to see intuitively. I'll say I cannot see an intuitive way. For me, it's hard. Like, anybody sees any intuitive way, I cannot see it, because only the mathematics tells me they are independent. Yeah, I think it's hard to see intuition wise. It's hard to see it, but mathematics tell that they're independent. I hope that by mathematics it's clear, and if I got any intuition by seeing the picture, but right now I don't think I am getting any intuition. These are independent. No, I cannot get any intuition. So it's better to leave it here. So mathematically we proved it. They are independent. Again, so one more thing to take away. So takeaway is this. Takeaway: do not go with your intuition. Do not go with the intuition. Why? Because it can be wrong sometimes. So it is better to go with the mathematics. So go with the maths. And sometimes if you can build intuition around it, it's good. If you can build intuition around it, it's good then. So, but if you go with the intuition, and sometimes you'll feel intuition tells me one thing, but when you check it mathematically, it will be other thing. So it is better to see it with the maths. Okay, then try to build intuition. If you give me, let's suppose, 10 minutes or so I can come up with an intuition around this. But it is the better part would be first see the maths and then try to build intuition, not the other way around. You have some intuition and you try to build maths around that, because maths obviously won't agree sometimes with the intuition, but intuition always has to agree with the maths. Is it clear? So what did I taught you here? My point was not to prove the thing. I was telling you how to prove things. So how to prove things? So if you are given something, write it mathematically. Also write what I have to prove mathematically. Then from the use this above argument somewhere. So that's the general proof. When you prove anything in life, if you prove anything, so you have premises, and then from that you infer something. Okay, and this was given to me. So this is a fact. I start with the fact. So I start with the fact and expand the fact somewhere, and then whatever was given to me, I used it somewhere. Okay, then I reached my claim. So if I claimed something, I'll reach my claim. That is a generic framework of the proof. If you have to prove something, so this is what you do. You have given something, and then first you will start by facts, and from that you will infer something, and you will use the given information somewhere. This is what is given to me. Then you will prove or disprove a thing that you are claiming, or you are not claiming that. Okay, how many of you understood the generic framework of a proof? How to prove things?
Yes, sir.
Okay, let me. So the next topic is conditional independences. Conditional independence. So what is the meaning of this? The meaning is that you have seen a probability of A intersection B is equal to probability of A multiplied by probability of B. So this means that two events are independent. Intuitively, we say that if one event does not happen, does not impact the happening of other event, it has nothing to do with that, then we call these events independent. Now we've also seen conditioning of events. If something happened, does it tell the information? Let's suppose now we have three events. Okay, we have three events. We have events like this. Event A, let's call this event A. Let's call this event B. Okay, this is our event A. This is our event B, and we'll call an event C. Let's suppose event C is something like this. This is my event C. Okay, this is my event C. These are my 3 events. So can I write the probability of A intersection B given C? Okay, so if I can write it like this, probability of A intersection A given C plus probability of, or multiplied by probability of B given C. So this will be the meaning of conditional independence if this thing is if this thing is right. Okay, this I have to tell you. So again I'll prove it. This is called as a prove by a counter example I'll give it. Okay, so here what I'm saying is, if you have an event pi, this is our sample space and there are 3 events A, B and C. So here if you see that probability of A intersection B conditioned on C, that is C happened. So if this is equal to this, so that means these conditionals are also independent. So if we have 2 independent events, then they are also independent on conditioning. Okay, now I'll give you an example. So let's suppose we have this event like this. We have an event A, we have an event B like this. These are my 2 events. Make it better. I won't prove every theorem, but here I'm teaching you how to prove things, so it's better to give it. And now C is here. Let's suppose C is like this. This is my C event. Okay. Now if C happened, okay, if C happened, if I had that level, so probability of A intersection B was equal to probability of A multiplied by probability of B. This was given to me that these 2 events are independent. Now I said that I'll say that these events are also conditional independent if probability of A intersection B given C was equal to probability of A given C multiplied by probability of B given C. So if this was the case, then I'll say that they are conditional independent. So now if you see from this picture, if C happened, okay, if C happened, and you can also see that this C happened over here, and I'll say that what is the probability of A intersection B given C now. Okay, if I say this, okay, now I'm telling you that C has occurred. So if C has occurred, now you can clearly see that now there is nothing common in here. So I am not taking this intersection part in the picture also. So that is by sure shot telling me that this intersection B, this is not happening if C happened. Okay, so this is not implying this. So this is not equal to this. So how many of you saw it from the picture? So what I'm telling you is that if this C happened, so if events are like this, if we have 2 events A and B and they have some intersection in between, okay, if these events are given that they're independent, so that I'm told that these are independent. So now I'm seeing that this C happened. Okay, let's suppose this event happened, this C happened. If this C happened, now I can by sure shot say that this A intersection B does not happen. So if this did not happen by just giving me the C information about C, so it somehow had the impact of now A and B. So it somehow had the impact of this. So if there was the impact on this A intersection B, then I can say that there is this conditional independence was not there. If C happened, it tells me some information about A intersection B, because that's how I construct the events. Okay, I took this C out of this. I took this A intersection B out of that C. So if C happened, I can surely say that A intersection B did not happen. So what is the meaning of independence? So independence means that by one event happens, it should not impact the happening of the other. It should tell me nothing about the other event. So right now, if C happened, if there is a scenario like this, you can clearly see that A intersection B did not happen. Okay, now you are seeing the dependence in there. So that means that if there is independence between 2 events, that does not mean that there will be independence in conditional of these events. Okay, that's what I want you to know. So I want you to know that conditional independence is not necessary. Okay, that's what I wrote here. So here I'll write it not equal to now. So that I showed you a counter example for this. Counter example is also a type of proof. If you give me something and you give a counter example for this, but giving example is not a proof. Giving counter example is a proof, because I am sort of giving you a thing which does not follow that rule. Okay, that is also a proof. And sometimes if you cannot find more examples, then you tell this is an exception. But if you have more exceptions, you said down this is not a rule. Okay, so here you saw that from the picture, you saw clearly that if A and B are independent, if construction is made like this, so this is called as proof by construction. Sometimes proof by construction, you construct things like that. We'll see a lot of proofs like this. So in deep learning, I'll show you some proof by construction and things like that. But here I'll also try like to some extent to show you how to prove things mathematically and how to prove things by different using different proof techniques. I hope that this is also clear. Okay, now we also have something called as conditional independent. We have pairwise independence So pairwise independence. So what is the meaning of pairwise independence? If we have, let's suppose, two events. If we have two events, suppose A and B. We have events A, B, and C. Let's suppose we have three events. So if A and B are independent, if B and C are independent, if A and C are independent, like we have all the pairs are independent of each other. So A and B are independent, A and C are independent, A and B and C are independent. If these pairs are independent, does it imply that they are independent as a whole? That does it mean that A, B, and C are independent? This is what you have to prove. Okay, this is your homework. Let's suppose I will give it a homework because it is already 8:25. So this is the last topic of this. So this is called as pairwise independence versus collection independence. So versus collection independence. So how many of you understood the question? So if we have, let's suppose, events A1, A2 till AN. If they are pairwise independent, if A1 is independent, A2, A3, A4 like this, but can I claim that they are also collectively independent? That's my question. The question being, if events are pairwise independent, are they also collective independent? So how many of you understood the question?
Sir.
You understood the question? This you have to prove to me before the next class, and then I'll just in the next class we'll just take some questions about independence and these things, and then we'll also see see different types of proof, that like proof of this, and then we'll start our own naive Bayes for machine learning. Next lecture, inshallah, we'll cover this algorithm. I think we are now having enough knowledge to cover this, so I'll just stop the recording.